Okay, so thanks to Sanjeev and other organizers for this meeting. So this work is an ongoing work. It's not, it's far from being finished, and it's with Ranjith, who is not here, and Aparna, who has a poster. I mean, some of you might have seen. So, okay, so before I go, let me, spend 1 or 2 minutes telling you that you might have, many of you might have heard about microtubules. These are dynamic polymers inside the cells, which, have to push and pull organelles, and, during cell division play a important role. They exert force and all that. Now, for the purpose of our talk, we'll think of one such microtubule in isolation. And in vitro experiments have been done, that not that it is just a theorist's imagination. And for, experimentalists have been working on this system in vitro for, past 18, 19 years, and they have lots of rates that they have extracted, how it grows, how it shrinks, and so on and so forth. But internal processes are not all fully identified. Even now, the hydrolysis rates are things that people sort of speculate, put into models, and then try to fit some macroscopic, observational data, and then try to say whether some model is correct or not. But just to give you a feeling that even after 18, 19 years, modeling is not in a state that people really know that what is the correct model for a microtubule. Even for a simple system like this, experimental data are not fully explained by one single model. And models exist at various levels. I mean, they can be totally coarse-grained, like something growing, shrinking, and switching from a growing to a shrinking state. They can be intermediate, like the ones that I will describe, in which there are monomers, which polymerize, depolymerize, and hydrolyze. And there could be even more detailed models in which you have the whole protofilament structure, 13 of them, forming a cylinder, and all sorts of detailed things. But for our purpose, this basic model. Now, how we got to this problem was that we were trying to improve on some existing model by introducing some small change in a new parameter in some model which was proposed in 2012, and trying to basically go towards seeing whether that improved model produces observational data a little more closely. But in the process, what happened was that something statistical physics of some statistical physics interest came around, and that is what is the talk about. Okay, so what is the simple model? I mean, this is the 2012 paper of Ranjith, Lacoste, and Kolometsky, and this is just simply this, that you have a polymer with monomers polymerizing and depolymerizing with a rate U and a rate WT. So these are these blue objects which are GTP tubulin monomers all in the solution, and that is what they polymerize. But as you see that this tube is not fully blue, there are some red. So that is what complicates matters. What happens is that at randomly at various positions, the GTP tubulin monomer goes to a GDP tubulin. So there is a hydrolysis, and because of that, the physical properties of these monomers are become different. I mean, their mechanical properties become different and all that. And as a result, if suppose a tip is exposed in which the tip is this GDP tubulin, like a red monomer, it depolymerizes very fast. This depolymerization rate is about 15 times higher than that. So if you have successive reds, then the tube will suddenly shrink. This is the famous dynamic instability of microtubules. Okay, so but it turns out that for matching various experimental data, people were making ad hoc assumptions, at least in this paper, for example, that if you have a tip that is from here, if you have two tubulin, GDP tubulin monomers, then something like a catastrophe will happen, and so on and so forth. We wanted to improve on that and said that let us make it something natural, that when you have a GDP tubulin, like a red monomer, polymerization becomes difficult. Okay, so there was a polymerization with a rate U. Now we'll say that when there is a red guy here, the blue monomer to come and attach will have a rate U prime. U prime is a lot lesser than U. Okay, so that's what I do. Now what's the question that I ask? It's a very simple question I ask, and as you understand, I mean, what is there? I mean, it's a polymer, it will either grow or shrink. So what you do is that if you change the concentration of the monomers, if they are high, it will grow. If the concentrations are low, it will shrink. That's the simple case. And so it seems that there would be, of course, some crossover from a growth state to a shrinking state, what is so interesting in that. But now we have this extra parameter, which is this rate of GDP polymerization. So as we make this rate U prime smaller and smaller, it becomes more and more difficult to polymerize if the tip has a GDP bound tubule. That's the point. And we want to vary this parameter, and we want to see as the system goes from a growth to a shrinking state, what sort of crossover does it have? And it turns out, interestingly, seems to be like a phase transition. So this is the old curve where these two rates that I talked about, U prime and U are the same. If you plot here, the, so let me go back once. So you have the X versus T plots here, right? So from here you can get velocities locally over some small stretches, and you can find the mean velocity also. You can find a mean velocity over a long stretch, or you can take small samples of velocity and form a probability distribution and look at various moments of the velocity. So here what is shown is that the mean velocity is going quite smoothly in the old case, and when I have this ratio like this, U prime quite small, I am having a jump like this. And if you look at this velocity as a function of time, in the old case, you see some occasional excursions to some faraway values from the mean. But here in this new case, what you see is that it is toggling between two states. Okay, so some bistability has come about. And if you take all these data and draw out simple statistics, then you find this probability distribution in the old case is like something at a positive velocity, a unimodal curve, which slowly shifts through 0 to negative velocity as the concentration reduces. But if you have the new model, you start with positive velocity. As you lower the concentration, at some point you have this bimodality, and then you jump to this negative one. Okay, so you can look at Binder cumulant, which is another sort of traditional signature to look at first order transition. If it is largely negative, that indicates that appearance of two peaks. So when you have just very large concentrations, you have just a positive velocity peak in the probability distribution. So you have the value 2/3. When you are coming to very small concentration, you have a value 2/3. In between, you have the transition. In the old case, you have a small bump. In the new case, you have a large negative bump. Okay, and this we have checked actually sharpens with system size. The data is not very good, so I haven't shown. But you see hysteresis also. As you ramp up the concentration at a particular rate, it goes up and then comes down along a different path. So having seen all of this in kinetic Monte Carlo, we also wanted to see it analytically. So you can do a mean field theory. So what you start out is, first of all, having site locations from the tip marked as 1, 2, 3, 4 like this inward, and then you define these kind of variables tau I, which take 1 or 0 value depending upon whether it is a blue or a red, GTP or GDP. And then the average value of this tells you that what is the mean value of having a GTP tubule in there. So you can have average tau I, and you can write down for all the tau i's such average tau i's such equations. And what you require is average tau 1 for calculating the velocity. Tau 1 is the mean likelihood to have a GTP here, and that if you know, and 1 minus that if you know, then you can just put in all the rates and get the mean speed. But you have to calculate this mean likelihood to have a GTP tubulin at the tip, and that is of course coupled to tau 2 and tau 2 to tau 3 and so on and so forth. And like these, you get equations where 1-point objects are related to 2-point objects and 3-point objects, and in the usual mean field sort of approximation, you decouple them as product of the averages. So if you do that, you can sort of see what are the solutions. So in the old model, you do find, like we showed in the kinetic Monte Carlo, a smooth transition with a single solution all throughout, going from a positive to a negative value. On the other hand, if you do now this new model, you do find a region where instead of one solution, this side, there are one solution, but in this middle region, you have three solutions. And then on top of the mean field theory, you can do a linear stability analysis, and we find the middle branch is unstable and the two are linearly stable. So this gives further support to this first order kind of picture that we have. So what is here is my summary, that microtubule dynamics, it seems to us, may have an underlying discontinuous liquid gas like transition. Actually, all this phase diagram of velocity, concentration, and that tip polymerization ratio are there in the poster, you can see. But the analogy with the liquid gas being the velocity is like the volume, concentration is like inverse pressure, and this ADP tip polymerization is like temperature. Now, of course, so the question is that you saw that this discontinuity is there for certain small values of u prime by u. Up to what value does it continue, and where does the transition vanish? So it turns out both from the mean field and the numerics that we have, it seems around 0.43 some value u prime by u that is terminating. But we haven't done any correlation calculation, so we cannot say whether the point where the first order is ending is a critical point, or as I was having discussion with Deepak, he suggested that who knows, maybe there is a second order line which terminates and that might be a tricritical point. So one doesn't know, one has to do further study, and of course finite size analysis is necessary. So this is very incomplete, but I thought that it's interesting. Thank you for your attention.
Thank you, Dibyendu. Questions?
This is non-equilibrium, so the detail balance is violated. Yes, so then we have to see if we really get a critical point after doing finite size, if we get those kind of exponents, yes. But it is 1D and it is, but still it is non-equilibrium, so we have hope that it's possible.
Since you have a smooth transition between growing and shrinking phases, how do you propose to identify the frequency of catastrophes, for example, to match with experiments?
Frequency of catastrophe, that will come from the time histories.
Okay.
For individual values of this u prime by u naught and concentration, you will have xt histories. And
okay.
From there you can draw out catastrophe frequencies. Right. And that Aparna has in her poster, you can have a look. The catastrophe frequency and versus concentration, we get very close to what this Walker experiment gets. In fact, that was the reason why we thought in the first place that we have made a better modification in the modeling compared to the previous literature. And this physicsy part came as like byproduct of that.
So can you also make a prediction for this frequency from your 1D model?
The values?
Yeah.
I don't remember. You remember? The frequency?
Or
their numbers are there.
Rescues also?
Yeah.
Because rescues and catastrophes in your model are kind of equivalent, right? I mean, one is not biased against the other.
No, but the rescues have a different concentration dependence frequency than the catastrophes. They are not following from each other. Okay. And so far as experiments are concerned, the catastrophe frequencies are doing quite well, but rescues we have still not got very well. I think the rescue story is much more complicated. And these days, many people are talking of other kinds of history dependencies appearing, which might be other structural changes happening to the tubulin. So I don't know, it may be more complicated.
Questions?
No, the reverse doesn't occur. So that is the reason I said that, it's a one-way process. So explicitly, there is no question of, trying out any kind of balance. So it's non-equilibrium in that sense, yes.
Thank you.